In the early days of the internet there was a war between OSI and TCP/IP. We already know who won the final battle and that the internet today runs on TCP/IP. But if that's the case, why do we still need to study and even memorize the OSI layers? The reason is that even though the OSI model lost as a protocol stack, it is still far better as an educational model because its clear layer separation makes it easier to understand, explain and troubleshoot network problems. And that's why network engineers refer to OSI layers when describing TCP/IP issues, and why you should take it seriously, understand it very well if you want to know what's going on under the hood, and simply if you don't want to be lost, especially if you work in networking or even cybersecurity. Please make sure to subscribe because there is a lot of network security and cybersecurity content coming up. Okay, so let's start with the basics. Both OSI and TCP/IP are models that describe how data travels across the network. They are probably the two most important and fundamental terms in networking. And you might ask, what exactly is a networking model? Well, this is just a set of rules, sometimes also called a networking blueprint or a networking architecture, that describes everything that has to happen to form a network. And it breaks down the complex process into simple steps represented in layers. These layers stack on top of each other, helping us visualize the flow of data in the network. OSI model consists of 7 layers and TCP/IP model consists of 4 layers. We will get back to this later. And now think of a networking model like building a house. You also need an architectural blueprint and you follow specific rules so you can be sure that the house has a solid foundation and won't collapse because everything fits together. It is the same with networking. If you buy a router from one vendor and a computer from another, you don't have to worry that they won't work together because product vendors follow the same networking model and they kind of speak the same language. Today, the single blueprint that everyone follows is TCP/IP, but it wasn't always like this. In the beginning, there was no universal model. Back then, vendors that built computers like IBM or DEC also created proprietary protocols that supported only their own product. And for example, the IBM, the biggest computer company in that time, in 1974, they published SNA networking model, which stands for Systems Network Architecture, and you don't have to memorize this one. So let's say that your company bought computers from both IBM, DEC, and maybe even one more company. It means that it had to create 3 different networks for each of these models. As you can see, it was a problem that had to be solved. There was a real need for one universal model that would be followed by everyone. And so the war began. The first vendor-neutral model was created by the US Department of Defense in the early 1970s. Their goal was to enable ARPANET to connect different networks together. Researchers at many different universities helped develop these protocols, and as a result, TCP/IP was established. It was practical, it was working, and it was funded by the military. On the other hand, there was a much more formal approach. In the late 1970s, the International Organization for Standardization, the ISO, started developing a model that we know as OSI, which stands for Open Systems Interconnection. Their intention was to create the perfect standard for the whole world. Throughout the 1980s and early 1990s, it wasn't clear at all who would win and take over the world of the internet. Many companies used TCP/IP and some other proprietary stack protocols, and they experimented with the OSI as well. However, by the mid-1990s, the TCP/IP had already become the standard and OSI fell in battle. Why did TCP/IP win? First, cost. Imagine this. The ISO actually charged money just to read the specifications of the official OSI standards. In contrast, the documentation for TCP/IP was completely free. Second, complexity. OSI was formal 7-layer model while TCP/IP was simple and very pragmatic. Third one, existing adoption. TCP/IP was already running on ARPANET and universities while OSI was mostly conceptual. And finally, flexibility. TCP/IP allowed improvements and changes while ISO was very bureaucratic and slow. However, as I mentioned before, you should know both models and their terminology for network engineering discussions and also if you're preparing for the CCNA. The TCP/IP is defined in documents called requests for comments, RFCs, and in RFC 1122, the 4 layers for TCP/IP are presented: application layer, transport layer, internet layer, and link layer. It also states that a host typically must implement at least one protocol from each layer. So as I already mentioned before, these layers make it easier for us to understand how data moves through a network. Each layer has its own responsibilities and is implemented by one or more protocols, and generally each layer provides a service to the layer above it. For example, the application layer uses protocols like HTTP or HTTPS for web browsing or SMTP for email. This layer is not about the application itself, but about the network services that the application needs to communicate. The transport layer usually uses TCP or UDP. It is responsible for end-to-end communication, ensuring data travels correctly from one device to another. If we need reliability, like for loading a web page, TCP is used. In this case, every single element has to be loaded perfectly. If a packet is lost, TCP will resend it. If we need speed, like for a video call or online gaming, UDP is used. Here, real-time communication encapsulation is more important than perfection. If a few packets will be lost, the connection might get a little worse for a moment, but the call keeps going without breaking. The internet layer mostly focuses on IP, and some other example protocols can be ICMP. It's about logical addressing where routing happens, so it means finding the best path for the data to travel across the internet. And the link layer handles the physical connection and uses technologies like Ethernet or Wi-Fi. It's okay if you don't know some of these protocols yet, you'll learn them as you go deeper into networking. And now let's also talk about the 7-layer OSI model. The first 3 layers from the top, application layer 7, presentation layer 6, session layer 5. In the TCP/IP we had all 3 layers combined into the application layer. And honestly, in most cases you will probably just refer to them as the application layer without worrying too much about the differences. But let's break them down anyways. Application, the layer that end user interacts with directly. It provides the network services to your applications. And we have here for example HTTP for web browsing or SMTP for email. Presentation. Think of this one as a translator, so it ensures that data from the application layer is properly formatted and encrypted, so for example SSL TLS encryption. Session. This layer is like a manager, so it establishes, maintains and terminates sessions between 2 computers or hosts, and in practice the session layer is rarely implemented as a separate layer, which is why the TCP/IP model is more practical and OSI model is more conceptual. The next one is the transport layer 4, which is exactly the same as in the TCP/IP model, so here we have the TCP and UDP protocols. Then we have the network layer 3, which is also the same as in the TCP/IP model, but instead of internet we call it network layer now. So it is again logical addressing and IP addresses. And the last 2 layers are the data link layer and the physical layer. In the TCP/IP model we had only one link layer, and here we divide it into 2 separate ones. Data link. This is where switching happens, so we talk about MAC addresses here. Remember, whenever we talk about IP addresses, it is always layer 3, and when we talk about MAC addresses, it is layer 2. And that's why sometimes we say that switch is usually a layer 2 device and the router is a layer 3 device. If you're not sure about this and about what is a MAC address, then I recommend my video about switches where I explain this. Physical. This layer deals with the actual hardware. It is responsible for transmitting raw bits over the physical medium such as cables or fiber optics. And now a little insider info that you won't find in the textbooks. So you might also hear sometimes about 2 extra unofficial layers that you've likely never heard of before. Layer 8, which refers not to the computer but to a person. So if you hear someone say we have a layer 8 issue, it means that the user simply made a mistake. And there is also layer 2.5, and this one refers to MPLS, which is multi-protocol label switching, and it's something between layer 2 switching and layer 3 routing. This is just a strange protocol that doesn't really fit into the OSI model, so we talk about layer 2.5 here. But it's a bit more advanced topic and also not in the scope of this video, so we won't cover it today. And finally, let's move to the last part of this video, and actually in my opinion the most important one, encapsulation. Without understanding this, the layers are just a list of names. Encapsulation is the process that describes how they actually work together to move your data across the network. And before we dive in, there's one term you need to know: PDU, Protocol Data Unit. This is just a general term for the package of data at any specific layer. When we send data, it moves down the layers, it gets encapsulated in new headers, and the PDU name changes. Okay, so let's go through the whole encapsulation process now. At the application layer, the PDU is simply just called data, and the headers will depend on the protocol used, for example HTTP. So we have our data in the application layer, let's say after the request from the browser. At layer 4, the transport layer, we take that data and we encapsulate it with a transport header like TCP. Now the PDU is called a segment. A side note, the PDU at layer 4 can be also called a datagram when the UDP protocol is used, however it's completely fine just to use the segment as a generic term for both. At layer 3, the network layer, we take that segment and we encapsulate it with an IP header, and now the PDU becomes a packet. And now let's stop for a moment to understand the flow of what's going on in here. At layer 4 we had the segment with its headers, and now we are adding even more headers on top of that. At this stage in the network layer we are adding the IP header, which contains the source IP address and destination IP address, and actually many other things as well. So at this point our PDU still contains the original data from the application layer, it also still contains the transport header, for example TCP header, and now it has also IP header as well. So the PDU is growing, and that is exactly what encapsulation is. And next, at layer 2 we take that packet, encapsulate it with another header and something that is called a trailer here, so it's a source and destination destination MAC address basically, and the PDU becomes a frame. And finally the physical layer takes that frame, converts it into bits, electrical signals or light pulses to travel over the cable. So basically what happened in here is we took the data at the application layer, put some headers around it at every layer, we encapsulated it, and finally at physical layer we transferred all that data, all those headers to another computer across the cable, and when the receiving computer receives those bits, it will decapsulate it, so it will simply reverse the encapsulation process. It moves up the layers, stripping off the headers one by one. So the physical layer receives bits in the form of electrical signals or light pulses, then data link layer reconstructs the bits back into the frame, and after using its information, it removes the frame header and trailer because it doesn't need them anymore. Then the network layer handles the packet, and after processing the IP header, it removes it. Then at layer 4 the segment header is processed and then removed as well. And finally the data is retrieved at the application layer. And this is what decapsulation is. I know this was all a lot of information. Please let me know in the comment if my explanation was clear and if I could improve anything. Also, if you found this helpful, please hit the like button. It really motivates me to create new videos, and don't forget to subscribe so you don't miss the next one.